do this. Okay. So let's start with this example. And again, really quickly, I'll get the three derivatives that we want. So F1 over here. Do you see the problem again? Look, if I go and work it this way, I will get here 2x, okay? As you can see, for the inside part. And then for the ln, I'll get 1 over x squared. That will leave me here with, as you can see, 2 over, 2 over x. And if I'm doing a Maclaurin series, okay, this will diverge to infinity. You see that? That is a big problem. So for some functions, what I'm trying to say is you can't use this trick, or at least directly. It's only, again, when you do specific functions that this trick will work to. So it's harder to integrate Taylor series than it seems. So this example here is kind of a bust the way it looks like right now. I could technically go in and change this maybe to u right now, but even if I did so, the problem persists because you got here, okay, the derivatives of this are 1 over u, okay, which you have yet, if you evaluate again at 0, diverges. So that's a problem, as you can see. So we need another example, is what I'm trying to say. What if we did, let's say, some kind of radical here, maybe like 1 plus sine of x. Or actually, let's make it a little harder. 3 sine of x squared. Okay. Again, notice what's going on here. Notice what's going on. This function, if I start taking derivatives, look what I'm getting. I'm getting 6x and then cosine of x squared. If I plug in 0 again to do the Maclaurin series, I get a big fat 0. But if I make a u sub, that here my x squared is going to turn into a u, right? I have my original function in terms of u right now written like this. It's 3 sine of u instead. And now if I differentiate this guy a bunch of times, look what I'm getting here. I'm getting 3 cos of u. The second derivative here would be, let's say, negative 3 sine of u, and so on and so forth. You see what's going on now, the difference. The next derivative would be negative 3 cos of u, and I'll do one more for good measure. This would be positive 3 sine u. If you plug in now to do the Maclaurin series, if you plug in a value of 0, center it at 0, the original here, 3 times sine of 0, that is 0. Okay. The second term, though, f prime of 0, 3 times cos of 0, that is 3. And the pattern here continues, right? So this here is going to be 0. This here is going to be negative 3. And the next one's going to be 0, and so on and so forth. So when I combine all of this to get f of u right now as a Taylor series, I got to fill this up. But we're working in the u world, of course. So f0 evaluated at a over 0 factorial times x minus 0 to the 0 power, that I've already shown here is 0. So this term is gone. First term is gone. Second term, okay? And we can write all of them out. But the second term here, f prime at 0 over 1 factorial times x minus 0 to the first. We've proven that this one is 3. Okay, this one here, this thing here is 3. Okay, and we can continue for the rest of the terms here. F2 of 0 over 2 factorial, x minus 0 squared. This, though, however, is 0. And you keep on going, right? F3 of 0 over 3 factorial, x minus 0 cubed. This we proved again is -3. And the last term again doesn't exist, so I'm not even going to write it down. My Taylor polynomial then, centered at 0 for u, f of u, is 3x minus 3, or no, 3 factorial here is 6. Minus 3 over 6 is minus 1/2 x cubed. Beautiful. Now I'll need to evaluate the error of this, okay? I'll need to evaluate the error. So since the fourth term here is gone, okay, I'll need to look at the higher one, at the fifth one. Okay, 3 sine of u will be differentiating to 3 cosine of u. That's going to end up giving me here, again, if I plug in 0, it's going to give me 3. No surprise. We'll need that for the error, the last derivative here. This is going to be for Taylor's inequality. But that's what I have so far, okay? This is what I have. So where do I go from here? And why have I used x's instead of u's is because I'm not really being careful. These are all u's. There we go. All right. So, okay. Making the substitution that u goes to x squared, okay? Making this substitution changes the bounds of the integral, okay? If right now, -1 over here, we go to x equals -1, okay? The u here goes to 1, and so it does over here when we go to 1. It approaches the same value. Okay, that doesn't mean we can't integrate it, but here's something interesting. That's why I hate picking examples myself. What I've picked here is an odd function, okay? You know what this means? When the bounds are symmetric and we have an odd function that we're integrating, do you know what happens? Do we remember at all? Math 117? It vanishes. The integral will vanish. That's what happens. So sadly, I need to pick a little bit of a different interval here instead of making it symmetric, because the integral will vanish if we put symmetric bounds on this. So I might go with, I don't know, maybe like -1/2 here so that it doesn't vanish. If I do that and make the change here, u goes to 1/4. Fair enough. Okay. So we have this, and our interval for u is 1/4 to 1 right now. All right, we got what we needed. So now Taylor's inequality time. Okay, what you have here is not f of u exactly. You have the fourth Taylor polynomial of that function. It's not f of u exactly, right? It's the fourth Taylor polynomial of that f of u. Okay. F of u is this originally. This is f of u, and this is the fourth order approximation. Okay, so yeah, you can say that they're approximately, again, that's the idea, that we're approximating this to be equal to T4 of u. But be mindful of that. So now I'm going to go in to the Taylor's inequality and say, okay, R4 of u needs to be right now smaller than or equal. All right, here comes the m value, which is, it's going to be, remember, the fifth derivative here now, evaluated at some z, which is going to maximize this quantity. And then we're dividing by n plus 1 factorial, n plus 1 factorial, which means 5 factorial in the denominator, and then multiplying here by x minus a being 0. And again, we have here, I don't know why I keep writing x. I need to stop that. It's u, okay? U minus 0. And the power here is going to be n plus 1, so 5. Now, okay, let's write down what these are actually going to be. 5 factorial. 5 factorial, okay, 5 times 4 times 3 times 2 is 120. We have 120 here. And this guy, what do we do about this guy? We have the fifth derivative. We can go work on the side here what we can do about this. So f5 of z, bring him in, 3 cosine of u. 3 cosine of u. Our interval for u, remember, is or 1/4, excuse me, and then 1. That is where our u is going from. Is cosine negative during this interval? And this is all in radians, right, that we're plugging in. So is it negative? Cos of 1/4. No. And cosine of 1 again. I got to be careful. Cosine of 1. They're all positives. So we don't need to take the, if we're doing this, we don't need to take the absolute value of this at all. So this is what you have, okay? And your cosine function during this interval, okay? Let's figure out what it looks like. 1/4 and then 1. Okay, so cosine of 1, what is that angle? What is that an angle right now? Let's just convert that to an angle real quick so I can understand where we are. 1/4 radians or 0.25 radians. What is that an angle? We have pi radians here and 180 degrees. So that is 0.25. 1 second here times 180 divided by pi, about 14 degrees. So we are basically between 0 and pi over 2 over here, yeah. So we are seeing the cosine do this thing. Like this. Yeah, 1 radian here would be 57 degrees. So yeah, we've lined it up pretty well. That's how this cosine function looks like. Okay, between this interval. So if someone was to ask you again, where is the largest value of this cosine function? Is it at 1/4? Is it at 1? Is it somewhere in between? What would you tell them? Which value of u over here? Only between these two numbers. Remember, only between these two numbers. Which value of u maximizes the output here? Kelly?
1/4.
Yeah. So this, if we want to pick a z value that maximizes this derivative between that interval, we pick here the 1/4. So 3 cosine of 1/4, and that will give me right now, I don't think that's a special number, 3 times cosine of 0.25. Make sure you're in radians. It's around 2.9. Yeah, 2.9, I'm going to say. I'm going to write it a little bit better. So I'm going to say this is around 29 over 100. It's better to write it this way because it's going to go straight back to the inequality now. There it goes. So we have the top there, 29 over 100. The bottom is 120, and this is u to the fifth. So we've got in total 29 over 100, as you can see, times 120, which is 12,000. And then u to the fifth. There we have it. That is our error. And so how are we going to apply this to the integral now? All right. Bear with me. So again, the size of the error we have found. So that means if we combine the info right now about T4 and the remainder, f of u can be thought of as the fourth order approximation plus or minus this error. That's it. So we're going to put in right now 3u minus 1/2 u cubed, and then plus or minus 29 over 1 or 12,000 here, u to the fifth. There we go. This is actually now f of u. Beautiful. Oof. Okay. All right. Finally. So if I go now and integrate this, all right, my job again is to integrate this now. Again, between certain bounds. So like 1/4 and 1 for x, sorry, 1/4 and 1 for u. Okay. And again, that's all I need to do here. That's all that remains. I got to integrate this guy now. But before I do the integration, I will switch to the x world. So now we go from negative 1/2 to 1. F of u is going to be these bad boys over here. But we're going to change them all to x. I guess I haven't done that yet. So keep the bounds the same. I haven't switched to the x world yet. So we're bringing in this. Okay. Now we're going to go back to the x world. So we're going to have here from negative 1/2 to positive 1. U is x squared, I want you to remember. So we have 3x squared minus 1/2 x here to the sixth right now, plus or minus 29, okay, over 12,000 x squared. Wait, this was u to the fifth. Excusez-moi. Yep. So u to the fifth, if you replace u with x squared, you get x to the 10th power. There we go. And now we're going to integrate this whole thing. We're going to get here 3x cubed over 3 minus x to the 7 over 14 plus or minus 29. Okay, this is funny here, the number. 11 times 12,000. That's a very big number now. 132,000. And then this is going to go to x to the 11. And we're evaluating this now from negative 1/2 to 1. We have the error. You see it's carried through the integral as we go through. All right. 3's cancel. So for your evaluation now, we have here, let's see it. 1 cubed minus 1 to the 7th over 14 plus or minus 29, 132,000, and then 1 to the 11th power. Then you take away, okay, let's do it carefully, negative 1/2 cubed, that is negative 1 over 8, okay, minus, why are these so disgusting numbers? Then again, I made up the example, so I apologize. 1/2 to the 7th power, so 2 to the 7th power, let's see what that gets me, 128, okay, 128, and then times 14, that is 1792. Okay, so I get here minus 1 over 1792. All right, and then plus or minus here 29 over this, and then negative 1/2 to the 11th power. That's going to get you 2048. Okay, so we got 1 over 1024 times 2 is 2048. Yep. That is 1 over 2 to the 11th power. And of course, it's negative 1 over 2 to the 11th power. Oof. Okay, so you can see now 1 plus this guy over here plus 8 over 8 is what remains. We're going to write it like this, 1 plus 1 over 8. There's no easy way. You gotta evaluate these as integers now and decimals. Like, you gotta use your calculator at this point. I can't keep them separate anymore. Okay. So sadly, yeah, we have to do that. So my overall result here is going to be 1 plus 1 over 8 minus 1 over 14. Okay. And then plus 1 over 1792. It's going to be a tiny number, I guess. All right, so you get here 1.054 plus or minus. This term dominates compared to this one. Like, look how much smaller this is going to be here. It's going to multiply 132,000 2,000 times. So might as well just keep the first one, not even bother worrying about the second one. So that is this plus or minus 2.19. It rounds to 2.2, honestly, times 10 to the negative 1, 2, 3, 4. And that's it. That is your integral with the associated error in there. That was painful. Okay. That hurt me emotionally. But that's how you do it. We can do the other one if you want. But for the sake of time, I wanted to show you a separate example. Since we have Kelly's, I can give it to you. We have the file. It has the solution on it. I wanted to show you a separate example. So not all of them are you able to integrate like this. And be careful, because you might need to do a substitution, because the Maclaurin series might not even let you center it at 0. Like, when you center it at 0, the derivatives might vanish, for example. That's the thing. Okay. Now, I might do Kelly's as well, depending on time and how you guys are feeling. But I have so many more things to talk about before we actually finish. So let me get to that. And hopefully we have time to squeeze in Kelly's integral as well. Okay, the other topic. Let's go and talk a little bit about big O notation, because I have not even touched on that. Okay, so sometimes, again, they will ask you to write Taylor series and then for the terms, again, that we are not including for the function we're doing the Taylor series of, it might tell you, oh, so what is the highest order of the error that you are ignoring right now? How is your Taylor series bound above and below? So let's see how we could pull this off. Okay, to start off, I will do some examples from the ones that we've been provided. So let's see one of them. One of them here is, there's a function, f of x. We have x times cosecant of x right now. And the goal of this is to use, let's see, the 7th order Maclaurin series. Plus big O notation. That's what we want to do here. So we want to approximate this function using the 7th order Maclaurin series of this. We're going to be clever because I'm not going to sit here, and so should you. You're not going to sit here and take 7 derivatives of this right now. Okay? That's painful. Okay? And then evaluate them at 0, yada, yada. That's painful. There has to be a better way. So I notice here that this is a composite function. There's x over here. There's cosecant of x over there. And another way I can think of this is, well, I know cosecant is 1 over sine. And you know what? I know, or at least you will be given, the Taylor series of sine. I don't know it off by heart, but I can do a quick Google search. And again, you should be given, if you're asked a question like this, you should be given the Taylor series of sine. Okay, Maclaurin, rather, series of sine. Okay, it is an alternating series from what I see here, -1 to the n. Sine of x is -1 to the n. And we have here x to the 2n plus 1 divided by 2n plus 1 factorial. Okay. Make sure, again, we're doing it correctly. And it starts at n equals 0. So this is how this is the Maclaurin series legitimately of sine. Okay. So, well, obviously here we're dividing by sine, right? So we need to think about how we're going to do this right now. We are dividing by sine. And if we are doing so, I should put in the first term, the first 7 terms again for this approximation. So sine of x to the 7th order, I guess. We can start plugging in numbers here for n. So -1 to the 0, okay? And we have here x to the first power over 2 times 0 plus 1 factorial. That is the first term. And you do that for the 7 terms that they want you to. However, because this is annoying, I'm going to say 4th order. Okay, I don't want us to do the 7th order. So the next term here would be -1. So this is the n equals 0 term. This is the n equals 1 term. I'm just plugging in the value of n in there. So we get -1 to the 1 power, then x to the 3rd power, divided by 4 plus 1, so 5, not 4, excuse me. 2 plus 1, so 3 factorial on the bottom. That's the second one. And you keep on doing that, right? Till we reach the 4th order. So n equals 2, n equals 3, n equals 4. Okay. All right, n equals 2, -1 squared is just 1. The x here has a power now of 5th. The factorial on the bottom is 5 factorial. For 3, you get -1. Now we have x to the 7th power, and then 7 factorial on the bottom. And for 4, we have +1, x to the 9 power over 9 factorial. Again, the -1 here, I will suck it up to the front here, write it like this. And the -1 to the 0 is +1. So I'll write this like that. And we have 1 factorial on the bottom. This is it. Okay, that is the series up to 4 terms here for sine of x. So it's, this is approximately equal to that. Now, the next term would have been, as you can tell, negative x to the 11 over 11 factorial. That's the pattern here. But this guy here is of order x to the 11. You see, that's how we can write it. This is of order x to the 11. There are more terms here of order to the 13 and so on, right? Until you go to infinity, basically. But this is what is right now the smallest order that we're bound by. This is the smallest function that bounds this. Let me explain again. If we have a plot right now of this bit, call it t4 of x. If we plot t4 of x right now, might look something like this. This guy, the x to the 11 right now, what it's going to look like, it's going to look something like this. So let me exaggerate this a little bit. Okay. So when we look at these two functions, we look at the t4 of x. We look at t4 of x here, and then we look at x to the 11. Near zero, you can see how x to the 11 actually bounds us right now. And so does x to the 12, so does x to the 13, so does x to the 14, and so on, okay? They bound us more and more tightly. So that's the idea here. You're basically telling your audience with a big O notation, what is a function that bounds right now the function that you're analyzing? Find another function, a polynomial of some order that bounds, that actually restricts and confines the function you're working on near the actual place that you're working on. We're working on a Maclaurin series here for this example. So a is equal to 0. And so near 0, you can see again the x to the 11 power actually bounds us. We're always below in value to this, near 0. So that's the magical trick here. That's all there is to the big O notation. We're just telling your audience what is, again, a function that can bind or restrict, again, our function that we're working on. And this is a t4x in this case. Okay, so O of x to the 11 is what we put there. Now, that means that sine of x can be written as x minus x cubed over 6 plus x to the 5th, 5 factorial here again. 5 times 4 is 20, times 3 is 60, times 2 is 120, and so on and so forth, right? 7 factorial, 7 times 6 times 5 times 4 times 3 times 2. That will be 5,040 x to the 7. And then the other one here, 9 factorial, so 5,040 times 8 times 9 is a very, very big number, 362,880. And then we have x to the 9 there. And then plus other terms, that's what the O stands for, other terms of lowest order, x to the 11. That's it. That's how we would express our sign, or at least the fourth order approximation of our sign. We would say it's this plus some other terms here of order x to the 11. That's what's up. Okay. All right. So when we actually now want to find x over sine of x, it's the equivalent of taking x and dividing it by all this stuff over here, as you can see. Okay, so what did I want to say here? Basically, we can do the long division here if we want to. I hate doing long division, but you kind of have to when you're dealing with this kind of situation. So if we did long division right now, take a look at what would happen here. Essentially, I would start, let's start here with x to the 9 over this number. Should I do the long division? Is there a trick? Let me think one sec. Is there a trick to do? I don't think so. I don't think so. Sadly, you have to do the long division. Yeah, so I'll write this in order here. So I'll have 0 for x to the 8 minus x to the 7 over this. I'm just writing the terms in order. Plus 0 times x to the 6th. Plus x to the 5th over 120. Okay, 0 times x to the 4th. X cubed over 6. Okay, plus 0x squared. Plus 1 times x. And that's it. And we're dividing that right now. We're having x essentially divided by that. This is absolutely disgusting. Why do they make you do these examples? So you have x being divided by this, okay? And you're trying to do long division. So yeah, let me think about this for a sec. 1 second here. So what I would say here is you do the long division. I'm not going to do it, but the remainder, I think they treat with big O notation. So I'll explain what I mean. If you recall from long division, right? If we do, for example, like 10 divided by 3, okay, over here, and we use, of course, 3 here, times 3 gives us 9. We take it away from this and we're left, let's say, with 1. That's the remainder. So I just want to show you with color coding how the remainder theorem works. So essentially, this 3 times that 3 plus the remainder should give you the divider, or the guy that's being divided. Okay. So in essence, I use this whenever I do long division to remember what I do with the remainder. I always add it, right? And so 10 divided by 3 right now, yeah, it's again, we can use the big O notation to kill this guy and write the largest order of what he is. So 10 divided by 3 again. is going to be equal to whatever you got over here. So 3 plus the remainder divided by that 3 of the divisor. That's the remainder theorem. Okay. This we can find from the long division. It will be whatever lands here. And the remainder will be whatever lands here. And then, you know, dividing the terms, we can express this part here with big O notation of some power, okay? Some power. And this guy here is going to be a polynomial for us right now. We're going to have a polynomial plus some big O, okay? And that's what I think they've done, but they've only shown one step. I want to do a better example than this, okay? I want to do what happens if you do the opposite. If you have sine over x, okay? What happens there? That's what I want to show you. Something that actually we can do. So to do that example, okay, I don't need right now any of this stuff over here. One sec, because this glitched a little bit. There we go. I'll show you an example that you can actually do the long division. No problem, Leah. I forgot to tell her that I'm still recording, so she shouldn't worry. Okay, so what if you did this instead? Okay, because this is a much better function to work with. So you'd lay out the terms. That's what I would put on your exam. I don't know why they would do anything else. So you'd lay out the terms from the guy that you did the Taylor series on right now, and all of them would need to be divided simply by x here. So you would get overall 1 minus x squared over 6 plus x to the 4th over 120, etc. Okay. And then once I reached here, then my actual big O term would have dropped by 1 power. That's what happens. And that's what I would give them as the answer for f of x. I'd want you to do, rather than this example, I want you to do actually, I changed my mind and I want you to do this example. Not because we can't do the other one, but the other one seems, again, too cumbersome. So again, we wanted to do this example for 4th order. We want to approximate this to 4th order. So it's really simple. You have the Taylor series of sine, then you can write it out up to 4th order, n equals 4, I guess, over here. Yeah, and then from here, you understand that the next term is x to the 11. So the smallest, again, the minimum power of the polynomial that bounds us, that bounds this series here, is x to the 11. And then we take that and we basically divide it by x. Now that we do this, we basically divide everybody by x, including the power of the polynomial that bounds us. That's going to turn into an x to the 10 now. And we give them the answer like this. So no long division shenanigans and remainder theorems. So that's what I would do here if I were you, to practice this. So none of this shenanigans here on the left, on the right. Okay, I want to do one more. So I only have you, Pranav, left. They had to go, the girls, so I'm recording for them. Okay, I want to do one more really quickly here. See what we can find. All right, another example that we can think about. Let's say right now, Pranav, that I have a function here that looks like this. X squared e to the x, okay? That's what we have. And they tell you to find T4 or T3, let's make it even easier, T3, and give your answer using big O notation. How do I do that?
You could do the Maclaurin series expansion for e to the x, and then once you get that, you just stop at you need to stop at the big O notation for whichever one is larger than 3. So the one right below 3, you stop at that, and then you just write O to the x or whatever, and then you expand that using x squared.
Okay, so again, this guy has his own whatever Maclaurin series it has, right? We can very quickly have access to that. Whoops. Okay, that Maclaurin series here is, again, these should be provided to you, right? Whenever you're writing a test. I'm just looking for it. Okay, x to the n over n factorial, very nice and easy. So e to the x to the n over n factorial, 0 to infinity, I believe. Let me make sure. Yep. So again, if we want T3, then here we're going to, again, start plugging in the numbers, like you said. Okay, so we get x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x to the 2 over 2 factorial, etc. All right, and then other terms, like you said, other terms, because the next one's going to be to the 4th over 4 factorial, that we can replace with O of x to the 4th. Okay, and now if we're doing the multiplication here of x squared times e to the x, okay, all we need to do, in fact, here, Pranav, there's another way of seeing this. If this is the Maclaurin series of this, then if I want this function, I can just distribute the x squared into that Maclaurin series.
Oh, yeah, that's what I meant by expanding, yeah.
Yeah. So that here is going to give you now x to the n plus 2 over n factorial. Okay. And then you expand the first 3 terms. Well, actually 4 because, we start at 0. If you want to get T3, you got to stop at n equals 3. So if n is equal to 0, get x squared over 0 factorial. If n is equal to 1, we get n cubed over 1 factorial, and so on, right? X to the 4th over 2 factorial, x to the 5th over 3 factorial. And other terms here, because the next one will be x to the 6th over 4 factorial. So other terms here of power 6. Okay, so that's our answer. We put all these 4 terms there up to x to the 5th. And then we say that the smallest polynomial power that restricts us is x to the 6th. And that's it. Now, if you're tasked to multiply 2 Taylor series, let's say you've got here another example. If you're tasked to multiply here T1 of x, let's say it looks like this. Plus other terms, let's say of x to the 6th. And you're tasked to multiply it by another one that looks like this. Okay, so x to the 6 over 3 plus other terms of x to the 9. How do you do this one? If I actually want to multiply them? You know?
I think I have an idea because I saw this in one of the papers I was doing. So we have to stop at Okay, so when you're first you expand the first couple. So obviously you do like 1 into 1, 1 into x cubed, and then you do that for, I guess, each one. But then by the time you get to but when you expand the couple of the x into x, like for example x squared into x6 over 3, you'll get that the exponent is like too large for the Maclaurin, so you can ignore those variables. And then for the ones that are less than the one they give you in the question, the degree of whatever degree they give you, for example, in this example 3, you use those, you put the like terms together, and then you just simplify.
Okay. So yeah, it's like taking again the product between these guys, but then, you know, when you multiply this bit of them together, right? I can go over here and add that. Again, it's basically like doing unfoiling, but not quite. It's a little bit different, but it's basically like doing unfoiling almost. Okay. So, you know, this plus this, that's an order cubed again, plus that. And this. Try to make it easy. I don't want to make the examples painful. Then times this, so x to the 8 over 6. That. So don't forget to do, obviously, don't forget to do your O terms as well, because I just did. So this into that would just give me OX9. Okay. And then I started this multiplication here. So now I was here. And so I would get other terms of x to the 11 here from that one. Now I do this one. I'll break them if you want into brackets so you can identify, you know, which ones we did. Okay. Hold on, I made a mistake here. X squared over 2 times 1. X to the 7 over 6, and then x to the 10 over 24. Nope, over 18. Okay, and then the last one would be other terms x to the, wait a minute. I'm so sorry, Pranav. I think I'm still a little tired. So we were doing this one. So x squared over 2, x to the 5th over 2, x to the 8 over 6. And then this one would be other terms of power 11. Close that. Next one. Okay. And we're going to rearrange them again in order of increasing power. So next one here, x to the 4th over 6, x to the 7 over 6. Okay. X to the 10 over 20 or over 18. And then other terms of power 13. Okay. And then the last term, the last bit here. This will give me other terms of power 6, other terms of power 9. Okay, other terms of power 12. And other terms of power 15. That's my expansion. So over here, the lowest power that I see for my other terms is actually 6. That guy. This is x to the 9, that's x to the 11, x to the 13, and all of these other guys are bigger. So again, we're going to kill all of these in favor again of the lowest power, OX to the 6. Now let me make sure that that's the case. We don't do this wrong.
Sorry, I have a question.
Yes.
What about the x terms that are like larger than 3? Do we keep those or do we ignore those?
We ignore those.
Right. Okay.
So here, if I write my final answer, I would write it like this: 1 plus x to the cube ignored, plus here x squared over 2, plus x to the 5th over 2. That guy here, I think it was 8. Yep, so ignore. Plus x to the 4 over 6. Ignore, ignore, plus other terms of power 6. Lowest power is going to be 6. So it's 6 and above. So that's how I do the expansion here to merge the two Taylor series together. Okay, I pick again the lowest power of those errors, well, the O terms, and then anything that's above that I would ignore during the multiplication. But I do have to unfoil it properly to do this. Okay. So that's how I would multiply two Taylor series together if I needed to. Hopefully you never need to do that. Now, what else remains? For our topics, the only thing I have remaining here is using this guy, which is your building block for a power series, to derive other power series alphabet. For example, what if you want to derive the power series of this right now? What you need to do, since you know this, you can use this. You might say, what's the difference between here and here? And that is that x has turned into x squared. So then why don't I try to do that on the series as well? Turn this x into an x squared. So the power series of 1 over 1 minus x squared would simply be right now x to the 2n. That's it. That would be the first example, of course, that I could show you. Just as simple, again, as comparing and contrasting what's different here. Let's say they give you a Taylor series. Let's say they give you the one for e to the x that we just did. They say that it is from n equals 0 to infinity, x to the n over n factorial. And then I ask you, I go, what if I take here e to the negative x squared right now? You go, okay, what's the difference between here and here? What would you say? What did x turn into? It turned into a negative. Yeah?
Yeah, I think so, yes.
Negative x squared, that's what it turned into.
Yeah.
So again, I look at the x over here, and I know what I got to do. So e to the negative x squared. I need to replace this x here with negative x squared. And this is still getting raised to the power of n. So the Taylor series for this would simply be sum from n equals 0 to infinity, negative 1 to the n power times x to the 2n over n factorial. And you conclude it there. It is that simple. So you just look at what x had happened to it right now, and you go from there. Similarly, you can do more tricks with this. For example, if someone was to ask you, what is the Taylor, or the power series rather, of this guy? You probably don't know where to start, but the derivative of this, we kind of know. It is 1 over 1 plus x squared. Okay. And the Taylor series of this, or the power series, whatever you want to call it, the power series, I can find. How? By using the building block. Using this guy. This is the building block of all power series. So I go, okay. This guy here and this guy here differ by what? X turned into negative x squared. Again, x must have turned into a negative x squared to go from here to here in this representation. Fine. So 1 over 1 plus x squared should be the series from n equals 0 to infinity. And we change this again into a negative x squared. And you can see where this takes me. So this is going to be right now negative 1 x to the 2n. That is what the power series of this function is. But I'm not done yet. This is the derivative of the function I'm interested in. So if I want the actual function, I need to do what? What do I need to do to all of these? If I have the power series of the derivative of the function I'm looking for, what should I do? How do you undo this, Pranav? Do you have it?
No, I'm not sure.
By integrating. Okay, if you integrate with respect to x, you'll get what you want. This will go away. So basically, you're going to get that the tan inverse of x is the integral of this series right now that you have determined. Okay, and the integral, again, it doesn't care about what this guy or the sum. It can literally dive in straight to the x right now, because that's what it cares about. You're integrating with respect to x. So it can dive into the sum like this. Doesn't care about this. Doesn't care about anything that has to do with n. It can dive within the sum like this. Can you tell me what the integral of this would be?
X to the power of 2n plus 1 over 2n plus 1.
Exactly. And that is the power series of tan inverse. You use the trick there. We basically took the derivative of this. Notice that the derivative you can relate to this power series very easily. So you found basically a power series for the derivative. That's what you did here. You found a power series to the derivative. And if you want to undo the derivative, you need to integrate. So you integrated that power series to get the original function. And that's what happened here. There's lots of these that they can ask you. Lots and lots of these. And provided with where you start from, you can use any power series that they give you and use it as a building block to build something new. You can use the one that we just did for sine over here. Okay, you can take that one. Okay, and look at the cool things you can do here. You can go use this definition, because this is predetermined, and someone's going to say, oh, what is then the power series of cosine? And you go, wait a minute, cosine. Isn't cosine like the derivative here of sine? Isn't that true? Yes or no? Isn't that true?
Yes.
So if sine is this, okay, if sine is this right now, then all I have to do is differentiate this. Like that. And that will give me cosine right now. So again, the derivative doesn't care about the n terms at all. It does not care. So it will hit only the terms that have x. You have here this staying unchanged. And then your derivative term will go and hit this guy. What's the derivative of this if you were to take it right now?
Would it be 2n plus 1 into x to the power of 2n?
2n plus 1 will come down. Yeah, you're dividing by 2n plus 1 factorial. Okay, and then you have x to the 2n remaining. So here you have 2n plus 1 over 2n plus 1 factorial. It's like having 5 over 5 factorial. 5 factorial, I've used this trick before. 5 factorial is like 5 times 4 factorial. I've used this trick before. So what we can do here, we can apply this little trick. So we say that the factorial on the bottom is 2n plus 1, but then we take the 1 away now. So 2n factorial. Now, this allows us to get rid of that ugly term right there. And we can write the series for cosine now. So -1 to the n, x to the 2n over 2n factorial. Done. You see, just by differentiating the 1 that we had for sine. So I'm showing you again different tricks you can use through derivatives, integration, relating again what changes happened on the x to the original power series that you're given as a building block to build the new function. And again, now that you have the cosine, your prof might say, okay, why don't you do me then what the power series of this is? And you go, okay, if I want to do now the power series of this, what's the difference between what I have on the left and what I have on the right? X on the left has gone to root x. If I want to write cosine of root x, it's the same power series, but with the substitution that x is root x, or again here, root x to the power of 2n over 2n factorial. And when you go on the next step, you simplify this a little bit. Let's end here. And then you have x to the 1/2 power times 2n. So obviously here,
yeah, x to the power of n, right?
exactly. That's the only difference. You got the new power series. So that's what I mean. It's you need to use the original and you build from that. You notice again the changes on the x, or you notice that the function you're working with is the derivative of another function that it's easier to find the power series of, and you go from there. This is really good stuff. And that's what I wanted the girls to see as well. Okay. I don't think I've left anything over here untouched. I'm just going to pause 1 second, see if you have any questions.